I am really pleased to have Dr. Anissa Abi-Dargham here. She's a SUNY Distinguished Professor in the Department of Psychiatry and Behavioral Health, the Lourie Endowed Chair in Psychiatry, and the Associate Dean and Associate Vice President for Clinical and Translational Science. She pursued her medical education in Beirut, Lebanon at St. Joseph's University. She later relocated to the U.S., completing her residency at the University of Tennessee in Memphis, followed by a research fellowship at NIMH, the National Institute of Mental Health. Her areas of expertise are in molecular imaging, pharmacology, schizophrenia, addiction, and translational science. I think one of the really special things about it is the way she brings really rigorous basic research methods to the treatment, development, and assessment of really complex, severe psychopathology. And as I've said before in other places, she does it with a level of humanity that is really inspiring. Oh, and by the way, she's also a National Academy member and has truly been a great asset to Stony Brook for the past 10 years. Her talk today, Decoding the Brain in Schizophrenia, Insights from Imaging Studies. She'll be a 25-minute talk. We'll have some questions after. We have the pleasure of having Dr. Mark Slifstein, the director of the Positron Emission Tomography PET Research Core and Professor of Psychiatry, to share a few words about Anissa before our presentation. I do want to say a few words about Mark. He also joined Stony Brook Medicine in 2016. He's worked closely with Dr. Abi-Dargham for 18 years, serving as the director of PET data analysis in her lab. More recently, he's expanded his focus to multimodal imaging, and he's currently the director of the MRI Research Unit at the New York State Psychiatric Institute. Dr. Slifstein has secured research funding from a range of pharmaceutical companies and charitable organizations and published over 100 research articles on these topics. And with that, I will bring him up to the stage. Thank you.
Thank you, Dr. Lajoie. You've covered a lot of the biographical information that I might have said about Anissa, so I'll be a little off the cuff and going in some different directions. Her lab at Columbia was the Division of Translational Imaging. It was a very active lab that through the entire tenure of our time at Columbia, using different imaging modalities to study the brain, using positron emission tomography, PET, to study the neurochemistry of the brain, using MRI to look at function and structure of the brain in psychiatric conditions, but with special emphasis on schizophrenia. And when she came here to Stony Brook, that tradition continued. Our lab is the Multimodal Translational Imaging Lab, and it's a similar line of research. We use positron emission tomography and MRI to look at the neurochemistry, the structure, the function of the brain. Anissa's research career has received much accolades, honors, and awards from her peers in recognition of the high level of her research. It's a long list, but some highlights are that she received the Lieber Award for Schizophrenia Research from the Brain and Behavior Foundation the Brain and Behavior Research Foundation in 2018. That is sort of that organization's equivalent of a Lifetime Achievement Award, and it's a very highly regarded organization. It's a very high honor to receive that. As Dr. Lajoie mentioned, she is a member of the National Academy of Medicine. She has been very active in another highly regarded organization, the American College of Neuropsychopharmacology, where she's been involved in the governance and served as president in 2016. And the work continues in Stony Brook, our lab works on imaging and other modalities to look at the brain in schizophrenia. So today she's going to talk about molecular targets and their functional domains in schizophrenia. Please join me in welcoming Dr. Anissa Abi-Dargham.
Good afternoon. Can you hear me? Okay, you can hear me, you can see me. That's why I'm next to the podium. If I was here, I'd be hidden. This is really a special honor. I want to thank Mark for introducing me, but I want to thank Monica and Carl for inviting me, and all of you for taking the time. I know you all are very busy, taking the time to be here with us today. I also want to thank Carl for all the amazing initiatives he's been taking with our university. You know, in the meeting prior to this, you could sense the energy and the vision and creativity. It's really special to have you as a member of Psychiatry, Carl. He's in our department. So what I'm going to do today is, give you a very brief kind of generalized overview of the work that's been happening in my lab for the last years/decades. It started a while ago. We developed the methods when I was at Yale, implemented many of those during the time at Columbia, and then continued here at Stony Brook. So I'm going to tell you the story of what the questions we had, the answers, and then give you some of the details. So our first question that is, what is schizophrenia, and why were we interested in schizophrenia? The answer is that schizophrenia is a global brain disease, and I'll talk about the details. How do we probe the brain in schizophrenia? It's by using multimodal imaging, as you've just heard from Mark, and I'll tell you how. What did we find? The main finding has been abnormalities in dopamine levels. And what is the significance of these findings? Well, it turns out that abnormal dopamine levels interfere with multiple brain functions. And that's really what leads to the symptoms in so many domains of function. What other systems may produce the abnormalities that we found in dopamine levels? And that really coincided with the move to Stony Brook, and we've been looking at the cholinergic system and the opioid receptor system. How does our work intersect with some of the drug developments or treatment developments, therapeutics, that have been happening in the field? And I'm going to give you some examples of actually where our work kind of overlays pretty well what is, at this point, cutting-edge research for therapeutics in schizophrenia. For those of you who are in a hurry, this is pretty much the story, but now I'm going to go in details. So what is schizophrenia? It affects 1% of the population, so it's pretty prevalent. It costs hundreds of billions of dollars to the US economy every year. It used to be called dementia praecox by the person who described it first, Emil Kraepelin. And that really captures what it is. It's like having dementia at an early age. Late adolescence, early adulthood, that's when it hits. It's a chronic illness with a deteriorating course. People never regain function once they're affected by schizophrenia to what they would have been at had it not affected them. Regardless of the severity of the illness, everybody kind of loses some function, which is very different from other psychiatric illnesses like bipolar or depression, where people can recover to some extent in between episodes. So what are the symptoms that we see? There is psychosis, which comprises hallucinations and different sensory modalities. Delusions, such as paranoia. Thought disturbances is when you're talking to a patient and things don't make sense, they're illogical. There are cognitive deficits, and they affect almost every cognitive domains. For example, working memory, our capacity to keep information online for a brief amount of time to make a decision, and then forgetting the information. Executive function, our ability to make decisions that are appropriate to our environment. Social cognition, our ability to read people's emotions to be able to react appropriately. And these are subserved by different systems in the brain. Reward deficits, anhedonia, which is the inability to experience pleasure. Mood disturbances, patients can have depression or excitement, and they can swing in between. Movement abnormalities. Patients with schizophrenia have catatonia, which is extreme immobility, stereotypies, purposeless, repetitive movements. So if you think about this kind of like collection of different symptoms, it's almost every function we have, moving, thinking, feeling, deciding, etc., is affected in schizophrenia. And that's really what made me think it's just a global brain disease. The whole brain is affected. And so you can think of that as there are multiple lesions in multiple brain regions, and that's how you'd get to this. Or it could be that a central mechanism, maybe a central circuitry that kind of brings all these regions together is affected, and that is kind of reverberating across all these systems. So I'm going to talk to you about this central linking mechanism that I think is affected, or at least where our research has pointed us to. Let me first, for those of you who don't look at the brain all day long, like some of us do, give you some of that nomenclature that I'll be using today, some of the verbiage. So these are cuts through the brain. This is a coronal cut, so it's kind of parallel to the face. And this is a sagittal cut, which is kind of in the midline. And you see the frontal, the cortex is the surface of the brain. You see here the frontal cortex in the anterior part. The posterior will be the occipital cortex. Beneath the surface, you have subcortical regions, such as the striatum, and behind it is the thalamus. And then deep down at the base of the brain, where you see the midbrain, this is the beginning of what becomes the spinal cord. That midbrain contains dopamine cells. They're housed there, and from there, they're going to project through the brain. Now, these are the same structures I just showed you, but this is a diagram I'll be using throughout the talk. So you have the cortical regions, frontal, this is temporal, subcortical regions, the striatum, pallidum, thalamus, and you have here the midbrain, which is the substantia nigra vitae, where dopamine cells are. These are all connected via the circuitry. The cortex projects to the striatum, and those green arrows that are glutamatergic projections, excitatory. From the striatum to the pallidum, you have GABAergic projections, which are inhibitory. Everything that is orange and red is GABAergic, which is inhibitory. So the way the circuitry works is that you have the cortex projects to the striatum. From the striatum, you have to the thalamus, and from the thalamus back to the cortex. So you have these cortico, striato, pallido, thalamo-cortical loops. These loops are important loops to organize our behavior across multiple domains. Loops for emotions, loops for cognition, loops for motor behavior. So the cortex, sends information to the striatum, which is going to process its information, maybe bring in additional information that are important, and then somehow make a decision that they'll send back to the thalamus, which will communicate back to the cortex. These loops that are so important for our behaviors are all very much modulated by dopamine. You see those blue projections that are coming from the midbrain. And these projections are divided up in mesocortical, which is to the cortex, mesolimbic to the ventral part of the striatum and regions that are involved in emotion processing, and nigrostriatal to the dorsal part of the striatum. In addition, dopamine is a transmitter. It's like a key. It has to interact with locks. The locks are the receptors, and for dopamine, there are 5 subtypes of receptors or locks, D1, D2, D3, D4, D5. In the cortex, D1 predominates. In the striatum, we have equivalent numbers of D1 and D2. So the main mediator of dopamine's effect in the cortex is the D1 receptor. This mesocortical projection is very important for cognition. It's been shown that dopamine via its receptor in the cortex sets the inhibition, excitation tone that is critical for cognitive performance. In the midbrain, dopamine cells firing dictates approach and avoidance. Basically, dopamine cells fire to something that is good or aversive that happens, or even to the prediction of what's going to happen. So it's kind of a teaching signal in the brain. One of the important things is the outflow from the striatum to the rest of the circuitry, and that's also modulated by D1 and D2. And we call these the go and the no-go pathway. So you have to think about it, that these 2 pathways are a little bit like when you're driving a car. You have an accelerator and a brake. The go is the accelerator, and the no-go is the brake. And you need to have a balance between these 2. Now, what's important is that if you have an excess dopamine release, a surge of dopamine, that's going to make the go faster, and it's going to impair the brake. And that's normal. You may need that to say, OK, I'm going to do this now. And if dopamine dips down, then the brake takes over. It's like, I should stop. But if you have excessive dopamine for a long time, obviously it's going to unbalance this go, no-go in the brain. Okay? When I started my career, we all had, I'm sorry that I have a dry mouth because I'm sick today. I don't know if you can tell from my voice. At that point, it was very well known that all antipsychotics are D2 drugs, and their dose is dictated by their affinity at the D2 receptor. So with all this background on dopamine and that information, it seemed to be appropriate to look at dopamine in the brain in schizophrenia to see what's going on. So one way is to use molecular imaging. This is kind of an illustration of a dopaminergic synapse. Dopamine is those pink dots. So we developed methods to look at dopamine, but we also put this together with other modalities to understand whatever we measure molecularly, what does it mean in terms of the circuitry and the behavior. And all that is to kind of inform the therapeutics. So I'm going to tell you about our studies with dopamine and then the newer one and even our kind of attempt at neuromodulation. So what did we find? This is the bottom line of what we found. Looking at dopamine with positron emission tomography, we found that one region in the striatum, the midsection of the striatum, had too much dopamine that was related to psychosis, while in the cortex there was too little that was related to the cognitive deficits. And in the midbrain, where dopamine cells are, there was a deficit. So there was kind of this disconnection where dopamine is in dysregulated in different ways in different brain regions. It's kind of a mess. So that, in a way, explained the symptoms, but left us with the question of how does this all happen? I also should mention that we found the more dopamine here, the more altered connectivity between these 2, the cortical striatal connectivity. This is just to show you a bit more detail about that. More dopamine in the striatum was related to more psychosis, better response of psychosis to antipsychotics, weaker connectivity to the cortex, and more perceptual bias, which I'll tell you a little about in a minute. In the cortex, less dopamine was related to worse working memory performance and worse activation of the cortex when they were performing the task in fMRI. So we ask ourselves the question, how do you go from excess dopamine striatum to hearing a voice? And that was one of the most creative studies we've done. We combined imaging dopamine with looking at how people process auditory tones. And so when we're hearing things, what we really hear is a combination of what we expect to hear and the stimulus. It's never just a kind of a simple recording of the stimulus. We call this our predictions or our expectations. If you are exposed to auditory tones that are short, predictably short, and then you're exposed to a longer tone, you will perceive it as shorter. If the tones are variable, they're sometimes long, sometimes short, now you will experience the target tone more accurately for as long as it is. So if the context is very predictable, it will influence you more. You will have certain expectations. It's going to influence your experience. If the context is uncertain, you'll have a more accurate perception. This uncertainty effect is missing in patients with schizophrenia, and it's missing in relationship to the excess dopamine. So basically, to give you the summary, more dopamine in the striatum actually increase the influence of the priors or the context on people. They lost this uncertainty effect, and that led to biased perception and more hallucinations. And that, in a way, could be kind of a cognitive target that people could work on in the future. Now, what other systems could be affected? We looked at two, the cholinergic system. Acetylcholine is a transmitter in the brain that is linked to attention and many other functions. You may have heard, there are receptors for acetylcholine, such as the nicotinic, muscarinic. Nicotinic, you heard, nicotine, right? That's what cigarettes work on. And because it's in so many places interacting with dopamine, we decided to look at that. The kappa opioid receptor system was also of interest to us. The opioid receptor system is kappa, mu, and delta. You're probably familiar with mu because mu agonists are things like heroin and carfentanil. But kappa is interesting because kappa stimulants, such as salvinorin A, produce psychosis. So we thought maybe there's something wrong with the kappa and it's overstimulating, overexciting dopamine, and that's what's going on. So we looked at that. And I'll just show you what we found again. For the cholinergic system, we found that more cholinergic terminals were associated with more pathology, more psychosis, and more cognitive deficits. Interesting. The next one is when we looked at the kappa opioid receptor system, we found more of these was associated not with more psychosis, as we predicted, but with more anhedonia, the inability to experience pleasure. And that also is interesting in light of the fact of what I'm going to show you soon. How do these intersect with treatments? Okay. I showed you how there was a deficit of dopamine in the cortex, D1 being so important in the cortex for cognition. This led to the fact that D1 stimulation, so enhancing D1 transmission, would be a therapeutic approach. So we undertook this multi-site study with Yale, Columbia, UPenn, and Stony Brook. 120 patients just completed the study. We're just currently analyzing the data. We gave patients 5 different doses, 4 of the drug and 1 placebo on different days. They would come in, take the drug, go into the MRI, and we look at the activation of their prefrontal cortex when they're on this drug to see if it's doing better and if their performance on the working memory task is better. So very exciting. We hope that we'll see a good signal, but I'll let you know. In terms of the cholinergic system, what was happening in the field at this point is really transformative. It turns out that many pharmaceutical companies are looking at muscarinic agonists, so cholinergic agonists at the muscarinic receptor, as treatment for schizophrenia. And this is historic because it's the first time ever that a non-D2 drug was approved for schizophrenia by the FDA. It's an M1, M4 agonist by the company Karuna that just got bought by BMS for $14 billion. So it's a very exciting time for people like us because there's a lot of energy in the therapeutic field. Many other companies are looking at M1, M4 agonist, positive allosteric modulator, different ways of stimulating those receptors. And it turns out that kappa antagonists are being developed for anhedonia of depression. And so we think now that this may be something that could be used for anhedonia of schizophrenia. And it may be that you cannot treat schizophrenia with just one approach. You may have to combine interacting at the muscarinic receptor with interacting at the kappa opioid receptor to address both positive symptoms, psychosis, and negative symptoms, such as anhedonia. We call anhedonia part of the negative symptoms. And then finally, the last piece of information and therapeutic development I want to tell you is this is a collaboration with neurosurgery at Stony Brook with Chuck Mikkel, using deep brain stimulation for auditory hallucinations. This is a collaboration with Johns Hopkins. Chuck Mikkel reached out to us. We provided a patient who had very severe hallucinations all his life, unremitting, non-responsive to any antipsychotic. He implanted electrodes in the brain that go down to the substantia nigra, and you turn the stimulation in these electrodes on and off. So this is what it looks like. Remember this diagram? So that is the substantia nigra part of the midbrain where dopamine cells are. So the stimulation is happening there. We think this is important because it's along those loops I have been telling you about. These loops link up actually the auditory cortex, which is here deep down in the temporal lobe, not deep down, actually on surface. And that stimulation across these loops, and especially in the nigra, which is here, may interrupt some kind of abnormal circuitry happening that's feeding into these abnormal phenomena. And so that is the locus of stimulation. And this is the result from this one patient. He went from a rating of 8 on a scale of 0 to 10 in terms of severity of voices to 0. Like the voices just went away. And he's been voices free for like 6 weeks now. It's almost like a miraculous recovery. So it's very, very exciting. Johns Hopkins want us to do more cases. We're advertising these results to solicit more support for this kind of research across 2 departments. So how did these all work? To bring you back to the initial accelerator and brake that I told you about, this whole circuitry that is kind of linked up all together, and where the flow determines go, no-go, approach, avoidance. Under normal conditions, you have a sort of equilibrium between these systems. When you have too much dopamine, the accelerator takes over the brake. You have almost like a brain on steroids that just can't, put stops to anything that is excessive across the board. And what antipsychotics do, or treatments that modulate dopamine, or treatment that interrupt this kind of like aberrant circuitry somehow, such as DPS, is basically re-establish the brake, put the brake back on in a normal way. That is at least one hypothesis that comes out of all this work. Obviously, it's difficult to pinpoint exactly what in the brain is responsible for the therapeutic effect, but that seems like a potential reasonable hypothesis. So I want to end by thanking my collaborators, my own group here at Stony Brook with people who've collaborated with me also since the days at Columbia. Mark Slifstein, Roberto Gill, who's our main recruiter for patients. Jared Van Snellenberg, responsible for the fMRI studies. Cliff Cassidy, who's done a lot of the work with the bias perception. Judy Weinstein, the cholinergic work. Greg Perman, working on neuromelanin, which is an MRI way of measuring dopamine that we came up with. Scott Muller, looking at all the addiction work. John Williams, the connectivity. Natalka, who just oversees a whole team of research assistants and manages the lab extremely well. Chuck Mikel and Sima Mofakam from neurosurgery collaborate with us, and I want to thank our collaborators outside of Stony Brook, especially at Yale, Columbia with Guillermo Horga, and the Transcends team. This is the D1 trial team with people at Yale, UPenn, and Columbia. I want to thank the funding agencies. We've always been blessed with continuous funding support from NIMH, NIDA, BBRF. But especially, I want to thank the patients and their families for volunteering to do these studies, which can be quite burdensome. But without that, we couldn't be doing anything here, and we wouldn't be able to understand what's going on with this devastating illness. Thank you for your attention.
Thank you so much, Anissa.
It's a great talk, really impressive. So it's really difficult to translate it from, humans started directly for addiction.
Get the microphone.
Yeah, okay. So what actually made impressive from your talk a lot, but what I'm most interested in is that the treatment for the stimulation. So I have two questions. One is that, what does it drive you to the deep brain? Because if I look at the literatures, most people are, for human addiction, stimulation study, they focus on prefrontal cortex, right? Because for TMS stimulation, but you all go to the deeper brain. So what's the difference between of those two stimulation mechanisms?
The stimulation, difference between TMS and DBS? Is that what you ask?
Yeah, also I think the brain region difference between prefrontal cortex and SN you're choosing.
Okay, so in the deep brain stimulation, what would be the difference between stimulating different sites?
Yeah.
Anyway, so the TMS, superficial TMS basically can give currents to the cortex. It cannot go to anything deeper than the cortex. We use a coil that can go down to the insula, which is a bit deeper than the prefrontal cortex. But anything where you want to go to subcortical structures, you need deep brain stimulation. The superficial TMS doesn't get to those. So then you need to put electrodes. Now, why the substantia nigra versus other sites? I was skeptical when Chuck Mikel came and said, we're going to put the electrodes in the nigra. I said, wait, why not the associative striatum? That was really where we see the... And he said, well, Johns Hopkins put that grant, just, okay, well, we'll go with it. I honestly was really surprised with the results. I was in the OR. I was asking the patient, okay, tell me, 0 to 10. 10 is the worst. 0 is the least. Where are you? And he went down from 8 to 6 to 5. And by the end of the session was at 4. And then the next week was 0. And he's been at 0. What that tells us is that maybe it doesn't matter where, that what matters is to get that loop. And that also in preparing this talk was like, I probably should just concentrate on the loop because the loop is really the issue maybe, because I would have predicted that the nigra is where you need to stimulate, but it worked, and it's we have a lot to learn. I think that the next approach would be to stimulate different sites across these loops and see if there are differences. Which site is the winner? In most people, this is a one case, right? So, do the work that will answer this kind of questions.
Hello. In the OR, when you stimulate the substantia nigra, does that have some other effects besides the reduction of auditory hallucinations?
I'm sorry, say that again. Did the patient have other? So we don't have the full data set. They have a full set of ratings, but this is, part of the trial. So actually what I'm telling you is our own little rating scale that we kind of improvised just to get our own quick response. So this patient had, in a way, mostly auditory hallucinations. So I wouldn't expect a lot of changes in other areas. But, I've seen him after he came back, and he will say things like, the room is silent. I don't know what to do. It's just, so that's the most drastic. I don't know yet what other things will change, and especially over time, because, once you silence the symptoms, there's a lot of work to be done with patients with schizophrenia. It's not like we just give them a drug, treat symptoms, and then that's it, we solve their problem. There's rehabilitation, social things that have to happen. Most of them have lost connections, have lost also skills. So they need to kind of relearn. There's a lot of work to be done, but we have to kind of treat the symptoms first to be able to get to the next phase. So I would imagine that even if not much has changed now, that this is the kind of landscape we need to be able to build upon and improve their lives.
Okay, so we thank Anissa for your talk.